Okay, last go round with electromagnetism. Uh, Remember where we are here. That let's imagine a situation like this. We've got just a wire loop, and you're looking at the edge of the loop. The loop is in a plane like this, and oriented like this, and then you're seeing just this edge of the loop, and you don't see the back edge of the loop. And it's sitting in a region of magnetic field. Magnetic field points straight to the left, or at least that's the direction of the magnetic field. It points inside the area that's defined by the loop, and that's the only area and the only magnetic field that really matters because we have this quantity called magnetic flux, field strength at all points inside the area that we're considering, and times the area. Remember, this area is only the area through which magnetic field is passing. In this particular case, it'll be the same as the area of the loop, but we've seen other examples where it's not the same. And then cosine of an angle, the angle is the angle between the field direction, which is pointing straight to the left this time, and the axis of the loop, which is also horizontal. So in this particular case, the angle is 0, and cosine of 0 is just plain +1, the largest possible value for cosine. So get the largest possible value for magnetic flux. And why is magnetic flux important? Because if it changes in any way, that means there is now a potential difference created in this loop, or we say it's induced, is the normal technical term. And now that there's a potential difference, that there's an electric field always associated with a potential difference, and when charged particles in the metal here in the loop feel that electric field, they feel a force and start getting pushed around, start moving, and they become current, a current that's induced current because it was caused by the induced voltage. Well, here's the basic law of current. Any current, the induced current in this case, is just equal to the potential difference that started it moving, the induced potential difference in this case, divided by the resistance of whatever that current is moving through, resistance of the loop in this case. But because we have this relationship here, I can write the size, the magnitude of the potential change is just the same as the magnitude of the rate of change of magnetic flux. So let's look at a specific example here. Let's say we've got this magnetic field always pointing this way, but changing in magnitude. We'll say that positive field is field that's pointing this way. So always positive field, always field that's pointing that way, but for a while it's increasing, then stays constant, then decreases. And of course, if the field strength is changing, flux is changing. And if flux is changing, you get a new voltage appearing in that loop, and that makes a new current appear. So we're able to figure out what current as a function of time, what a graph of current as a function of time looks like if we know this and we know this about the magnetic field. That just to have our definitions clear, let's say that current, this is the front edge of the loop, the edge of the loop closest to us. If current is flowing this way through the front edge, that is in the back edge of the loop behind the blackboard, it's flowing like this, and then in the front edge of the front edge of the loop, the front half of the loop, on this side of the blackboard, it's flowing like that. So it's flowing so that at this point it's coming out at you, and then circles down, and at this point here, it's flowing away from you, flowing like this, or counterclockwise if you were looking at it from over here. And then a negative current will be current that goes just the other way. Or current that would flow clockwise if you were looking at it from over here. Okay, so in this particular case, these two factors are not changing, so that the rate of change in the flux is entirely due to just the rate of change in the field. And in fact, the rate of change of flux is just going to be proportional to the rate of change of field, because these factors are just constants in this case. So during this time, we have magnetic flux flowing this way and getting stronger. So the induction, one aspect of induction is Lenz's law. Remember that the induced field, or the induced current, like any current, produces a brand new magnetic field, different from this one. That brand new magnetic field, according to Lenz's law, always counteracts the change that got the induction process started. Well, the change was more field and flux this way, so to counteract that kind of change, you have to have the new field pointing the opposite way so that it cancels out the additional leftward field and flux. So increasing positive field means you've got to get flux flowing and new field flowing that way. Well, what kind of current, either clockwise current or counterclockwise current, what kind of current is going to give us field? And remember, we're always thinking about field inside the loop. What's going to give us field inside the loop that points this way, left to right? And remember, for that, we use this right-hand rule that connects current direction. Point your thumb in the current direction, and then your fingers will always curl in the same way that the magnetic field lines flow. So if you had positive current going like this, coming out at the top and then circling around and going down this way, now point your finger, or your thumb, in that direction. Thumb is coming out, and now thumb is pointing away from us. When you do that and you curl your fingers, and curl them like this, that tells us that the field lines are circling, the field lines are loops, the field lines are looping around like this. Or here, where the magnetic field is like this, the field lines are looping around like this, so that when your fingers get to the plane of the loop, they're pointing that way. A common problem is that in getting this stuff right is that people just are too timid about their movements. They'll just curl their fingers a tiny bit and think that's going to give them the correct answer. No, it won't. If you want to figure out what kind of field you have right here in the plane of the loop, you have to curl your fingers until they get to the plane of the loop. Curling them like that. See, at this point, right here on the edge of the loop that's closest to us here, up in front of the blackboard, current points down, and then keep on curling your fingers until they touch the plane of this loop, then you can see clearly that current like this, positive current, makes field that way. Okay, so we know that during this time we have positive current. And is that positive current changing or constant? Well, here's the rule. This is that positive current that's been induced, and it's just here, it's proportional to the rate of change of flux. Remember, in this case, it's only magnetic field that's changing, so the rate of change of flux is entirely due to the rate of change of magnetic field. And if the, here, it's a straight line, so the rate of change of field is constant. For every step in time, the magnetic field strength increases by the same amount. Or remember what we've seen from time to time ever since chapter 2, when you've got a graph of anything versus time, slope is the rate of change. Like for instance, in a graph of position versus time, slope is velocity, which is just rate of change of position. So constant slope means constant rate of change, which means this rate of change is constant, which means current is constant. Like that. And now, during this period of time, field is constant, so flux does not change. So the rate of change of flux is 0, so there's no electromagnetic induction happening. No flux change, no potential difference is induced, so no current is induced. 0 current, well, the field is constant. Now, here, the field is still pointing right to left, but it's decreasing. So let's think about what happens here. Decreasing field means, again, a current is induced, and that current is going to create a new magnetic field, and that new magnetic field has to counteract the change. In this case, the change being less and less field pointing to the left. So to counteract that change, you have to add in some field that points to the left to make up for the lost field pointing to the left. And how do you get field inside the loop pointing this way? Well, you have to have current that goes the opposite way from what we saw before. If here on the front side of the loop, the current is going like this, that is at the bottom, coming out, and then moving up so that at the top of the loop it's pointing away from us, that's going to give us, inside the loop, field that's pointing left to right. So my thumb is now following the path of that current. So right here, at the far edge of the circular loop, when the current is going this way, current is going this way, my fingers curl until they get to the plane of the loop, and I can see that now my fingers are curling and pointing this way, so the magnetic field in the plane of the loop is pointing this way, right? To get my fingers curling enough until they get into the plane of the loop, I want the fingertips to be in the same plane as the thumb, because the thumb represents the current in the loop. So the thumb is in the plane of the loop. So you get current that way, which we defined to be negative. It's got to be the opposite kind of movement from this. So it's a negative current, and it's also constant. Because just like before, graph of anything versus time, if you have that, the slope is the rate of change. Slope is constant, So the rate of change of magnetic field is constant, which means the rate of change of flux is constant, which means if rate of change of flux is constant, the induced current is constant. So constant and negative, but in this case, it's smaller current than it was here. How do we know that? Because here, during this time interval and this time interval, the amount of change in the field is the same, but during this time interval, it takes longer to make that much change in the field. So the field is changing at a slower rate. Right? This is a less steep slope than this, indicating a slower rate of change. So now, during this time, this is a slower, changing at a slower rate. In other words, this number is smaller. So the induced voltage is smaller. So the induced current has to be smaller. Okay. Now, think about something else here. Induced, in this particular case, what happened, there was a change in magnetic field, and that produced a new voltage. Well, if there's a voltage, or if there's a potential difference, there's an electric field. They always go together. So you could just as easily say that a change in this magnetic field produced a new electric field. It induced a new electric field to appear. So let's think of it this way. Let's imagine instead of the magnetic field changing like it, as was illustrated by that graph just a minute ago, let's say the magnetic field is oscillating like a sine or cosine function of time. Well, that again, in this case, the area stays the same and cosine of the angle stays the same. So the flux is always going to be proportional to the magnetic field. So if magnetic field is oscillating like a sine or cosine, then flux must be oscillating like a sine or cosine. And if flux is oscillating like that, it's changing. And if it's changing, that induces a new potential difference. And we could just as easily say that the changing flux induces a new electric field, because whenever there's an electric field, there's always a voltage, always a potential difference, and vice versa. Turns out that if the flux is changing, is oscillating, if the changing flux is changing like a oscillating sine or cosine function, the electric field that's induced will also be oscillating like a sine or cosine function. Actually, cosine or sine. If this looks like a sine, this is going to be a cosine and vice versa. But anyway, oscillating. That's the important part. Well, the electric field oscillates, so the force that any charged particle feels will oscillate. And so the way in which those charged particles get pushed around is always changing. Sometimes there's strong force in this direction, and then a half cycle later there's strong force in the opposite direction. So current is always oscillating. Sometimes there's strong current in this direction, sometimes there's strong current in the other direction. The current oscillates. That current, like any current, produces a magnetic field, and if the cause of that new magnetic field oscillates, that is, if the current oscillates, then the result, the magnetic field, will also oscillate. But here's the important thing. in this area here, whether we have a loop there or not, either way, changing flux in that area, whether there's a loop surrounding that area or not, either way, changing flux through that area creates electric field. Either way. And the interesting thing, the kind of amazing, surprising thing is that even if there's no loop to have current inside, the changing field still, the oscillating field still produces a new oscillating magnetic field, a new oscillating magnetic field in addition to, different from this original oscillating field that started the whole process. And at that point, we're right back to where we started. Right. So even if there's no loop and therefore no current, the amazing thing is that this step still happens. And then what have you got? You've got a field oscillating. So you're right back to this situation, except now this field is the new field that was produced by the oscillating electric field. But this new field makes new flux, which is changing. That new flux, which is changing, makes yet another electric field, which is oscillating, which produces yet another magnetic field, which is oscillating, which produces yet another flux which is oscillating, and so and so. You get on and on like that. You get a self-sustaining chain of oscillating electric fields producing oscillating magnetic fields that produce another oscillating electric field that produces another oscillating magnetic field, and on and on and on. And that is what we normally call an electromagnetic wave, light wave, infrared wave, ultraviolet waves, all that kind of thing. The one thing to notice here, in this case, this is an example of something that happens all the time, every time, without exception, when we're talking about electromagnetic waves. The magnetic field is in this direction, right? Horizontal and left to right. The electric field is in a plane perpendicular to that, right? We know that the electric field has to be in the plane of the wire because we know that when current is induced here, it's because the charged particles are feeling an electric force from an electric field, and they're not going to feel a force from an electric field unless there is electric field inside the wire. In other words, in the plane of the wire. But as I said, that electric field is there even if the wire isn't. So the changing magnetic field in one direction produces the new electric field in a perpendicular direction. That's always the way it works in an electromagnetic wave. The oscillating electric and magnetic fields are always perpendicular to each other. And furthermore, turns out, they are both perpendicular to the velocity of the electromagnetic wave. So 3 things there: velocity of the wave, electric field, magnetic field, all perpendicular to each other. For example, let's say you've got an electromagnetic wave, and let's say the wave velocity is this way. There's our symbol for something pointing out of the plane of the paper or out of the blackboard. Okay, the three important things that make up that tell us about the electromagnetic wave, velocity, magnetic field, and electric field, are all perpendicular to each other. So the velocity being perpendicular to the plane of the blackboard, that means the electric and magnetic fields must both be in that perpendicular blackboard plane. and they have to go like this, not just any directions in the plane of the blackboard, but they have to go like this. Because it turns out we have another right-hand rule that relates the direction of electric field, the direction of magnetic field, and the direction of the velocity. And that right-hand rule works exactly the same way as the right-hand rule for magnetic force. It involves thumb, index finger, and then the other three fingers rotated. So how it works is like this. Point your thumb in direction of electric field, index finger in direction of the magnetic field, and then rotate your other three fingers so that they're perpendicular to both the electric field, thumb, and the magnetic field, index finger. And then when you do that, your fingers will point in the direction of velocity. So in this case, what does that look like? So rotate other three fingers. And that gives the direction of the velocity. In this case, how does that look? Thumb in direction of the field, index finger in direction, thumb in direction of electric field, index finger in direction of magnetic field, other three fingers perpendicular to those. The other three fingers are now pointing straight out. That's the direction of the electromagnetic wave in this particular case. So just as an example, say looking at, remember these are oscillating electric and magnetic fields. So they go through a cycle. Let's see what this sort of thing looks like over one whole cycle. So, in time zero, when we first turn on, start watching, we take a snapshot of that wave. And at that moment, electric field points this way and magnetic field points that way. Then a quarter cycle later, with the time equal to 1/4 of the period, say these fields are both at their maximum values at this time. Well, any oscillating thing, if it's at maximum value at one point, a quarter of a cycle later, it's back to zero. Right? Remember when an oscillating mass was oscillating back and forth about equilibrium, if you start watching it when it's at maximum distance away from equilibrium, a quarter of a cycle later, it's back at equilibrium. So a quarter cycle later, this has gone from maximum to zero. And then another quarter cycle after that, or a half cycle after the start. Going through a half cycle, if you start at the maximum in one direction, half cycle later, you're at the maximum in the other direction. Like that. And the right-hand rule still works. Thumb in direction of the electric field, index finger in direction of the magnetic field, the other finger's perpendicular and they're pointing out, which was still the direction of the wave velocity. And then another quarter cycle after this, for t, time is half a period there, and then 3/4 of a period here. Well, at this time everything is at maximum value. Quarter cycle later, it's all gone, it's all back to 0. And then a quarter cycle after that, you've gone through 4 quarter cycles, you've gone through 1 full period, so the system is right back to the state where it started. Like that. So there's three aspects to this, these electromagnetic waves. Velocity, magnetic field, and electric field are all oscillating, and they're all mutually perpendicular. All oscillating, all mutually perpendicular, and they're perpendicular according, third thing, they're perpendicular not just any old way, but according to this right-hand rule. Electric field, magnetic field, wave velocity. One last thing, it not surprisingly, because the magnitude or the magnitude of an electric field and the magnitude of a magnetic field are related, which is not surprising because the electric fields are caused by changes in the magnetic field and vice versa. Specifically, and the relationship is pretty straightforward. The magnitude of an electric field at any moment in time is always proportional to the magnitude of the magnetic field. And this proportionality constant is just the speed of an electromagnetic wave, also known as the speed of light, since light is an electromagnetic wave. And that's, the number is, we use as 3.0 times 10 to the 8th meters per second. If you always use this number in meters per second, our standard kinds of units, and always use this in our standard kinds of units, volts per meter, or newtons per coulomb, either one is an acceptable unit label for electric field, then this automatically comes out in the correct units, which are called Teslas. Okay, so just one last example here. You can, that means there are some ways in which an electromagnetic field can exist and others that aren't possible. Let's say you got something like this. Let's say here's 3 axes, X, Y, and Z axis, right? And these two are supposed to be in a horizontal plane. And this is the positive Z direction, and this is the positive X, and the positive Y. Let's say you've got, at one point in time, an electric field that points this way, and a magnetic field that points this way. So that is the electric field is pointing in the negative x direction and in the positive z direction, and then the magnetic field is pointing in the negative x, or the negative y direction. So these two fields are in the zy plane. So the velocity has to be perpendicular to the zy plane. In other words, it has to be along the plus or minus x direction, and this rule will tell us which way. Thumb in direction of the electric field, index finger in direction of magnetic field, and then fingers rotate until they're perpendicular, and then they point in the direction of the velocity, which is going to be this way, the plus x direction. And remember, the magnitude of that velocity is always going to be 3 times 10 to the 8th meters per second. Okay, let's say we know the magnitude of this. The magnitude of the electric field is just 80 volts per meter. That tells us what the magnitude of the magnetic field must be, because they have to obey this rule. Magnitudes have to obey that rule. So electric field over speed of light, magnitude of electric field over speed of light is the magnitude of the magnetic field, which is 80 volts per meter divided by 3 times 10 to the 8th meters per second. And if that looks like a strange combination of units, but if you use all the standard units, no centimeters, no milliseconds, no millivolts, you will automatically come out with the right unit label for magnetic field. And in this case, it'll be about 2 2/3, or we'll round it off to 2.7 times 10 to the minus 7 Teslas. In other words, because this is such a big number, this will always turn out to be a tiny number of Teslas when compared with the number of volts per meter that you have here. Okay, let's look at just one last example here, a kind of a situation that you could not have. Let's say here's the x-axis again, and the z-axis, and then the y-axis. There's the positive y direction, positive x direction, and the positive z direction. And let's say, just like before, the electric field points in the positive z direction. And then let's say that the velocity points in the positive y direction. Okay. That means, since since this has to be perpendicular to both electric and magnetic fields, that means the magnetic field must also be in the xz plane, perpendicular to the y-axis. Let's say if you thought of something like that, a magnetic field like that, right in the xz plane, but it's got, say, an x component like that and a z component like that. That's wrong. That's not going to work. That can't happen. And it can't happen because it breaks one of the basic rules. The two fields have to be perpendicular to each other. And obviously they're not perpendicular to each other. They're only directions only differ by an angle like that, which is obviously not 90 degrees. So a situation like that could never happen. Okay, and then you'll try a few simple things about electromagnetic induction and electromagnetic waves in the exercises. One other thing that's worth noting: think back to way back when we were talking about traveling waves. Traveling waves carry energy. Every wave carries energy. And we can characterize the amount of energy with this number that we call intensity. And we found way back then that for any wave, its intensity was always directly proportional to square of the amplitude, right? Amplitude being the maximum value of whatever is oscillating. The electromagnetic wave is just another wave, so it obeys this rule too. Now, what in the case of the electromagnetic wave, the thing that's oscillating are two things: electric field and magnetic field. So the intensity of an electromagnetic wave is always going to be proportional to the square of one of the things that's oscillating, square of the electric field, or square of the maximum electric field, right? Amplitude. Amplitude is the maximum value of whatever is oscillating. So but it's not the only thing that's oscillating. Magnetic field is also oscillating. So, but being a wave, intensity of the electromagnetic wave is proportional to the square of the maximum value of whatever is oscillating. So we could just as easily say that. Since at any point in time, like the moment when electric and magnetic fields both have their maximum values, they have very, very different size values. Obviously, the proportionality constant here is going to be different from the proportionality constant here. Right? Whether you're looking at the electric field or the magnetic field, you're going to find you're going to get the same number for the wave's intensity, how much energy it's carrying. It's just that in both cases the calculation is a little different, and you see that in the equations in a text, equations 25.13. But anyway, the important point is that changing intensity changes because the amplitude of the electric field changes and the amplitude of the magnetic field changes. Of course, they change together because we also have this rule. So obviously, if the magnitude of one field changes, the other one is going to change its magnitude by the same factor. So you can try some of those questions.